My name is Mitsuhisa Sato from the Riken Center for the Computational Science. I'm going to talk about the supercomputer Fugaku, especially focusing on performance characteristics of the A64FX processor. This is a picture of the Fugaku. Public service has already started from the March this year. The Fugaku is the huge scale many core based parallel system with more than 150K nodes. The peak performance is almost half exaflops in a double precision, 1 exaflops in a single precision. This is the outline of my talk. First of all, I'd like to present the co-design effort of the A65X processor for the Fugaku in our project, flagship 2020 project. The flagship 2020 project is developed the supercomputer Fugaku, and S65X was developed by the Fujitsu and Riken in this project. And next, I'm going to talk about a performance result of the S65X, showing the result of the several benchmark, UK benchmark, and the open source HPC software, and the spec benchmark. And I'd like to give some comment on the performance tuning and power control feature of our system. At the beginning of our project, we defined 3 KPI, the key performance indicator as shown in this slide. The first one is the power efficiency. We have decided the maximum power supply to 30 to the 40 megawatt in our facilities. The second one is the effective performance of the target application. The performance of the benchmark was not our priority, that we expect 100 times faster than a K computer in few applications. This table shows the target application for co-design. This application is taken from our user project. We select these applications as a co-design. That we set the target performance as relative to the performance of our previous system, the K computer, under the power constraint. So that we set the 100 times faster target in 2 applications. One is the Genesis in the NVIDIA application, and the LATKF is the climate application and data assimilation application. And the third one is the ease of use. Our system has no accelerator like GPU. Our system is just a shared memory system. It is the many core processors and high bandwidth on-chip package memory, HBM. This makes existing OpenMP and MPI hybrid program ported easily. To develop the system, we need to decide many technologies and the architecture's parameters as shown here. And we have design target, 3 design target, and co-design was done to meet these targets. Especially, we need low power technology to get the maximum performance with the power constraint. First of all, let me give the overview of the Fugaku system and processor. Fugaku is the ultra-scale general purpose, the mini-core system. It has the more than 150K nodes, one processor per node. So it's mean 70 million cores in total. A65X processor is a processor designed for supercomputer Fugaku, and the instruction set is ARM 8.2 with the SVE. SVE is the ARM SIMD instruction set. The length of the SIMD is the 512 bits, and it has the two pipes for the SIMD in each core. The number of core is the 48 plus 2 or 4 core who are dedicated the cores to running operating system function. 48 core is divided the 4 groups. Each core has the 12 core. This is the NUMA node. We call this the CMG, core memory group. Cores in a CMG is sharing L2 cache, and the memory controller which is connected to the HBM2 chip. CMG is connected to by the network on chip. The memory is on package stacked memory HBM2. We have only HBM, no external memory. The capacity of the HBM chip is the 8 gigabyte, and we have the 4 HBM chip. So the size of the total memory is 32 gigabyte with 1 terabyte byte per second memory bandwidth. Interconnect is the TOF T interconnect. This is a six-dimensional torus topologies dedicated design for the scalable internet connect to the Fugaku. The standard programming model is the OpenMP and MPI hybrid program. The running one MPI process on each CMG. OpenMP process is running on each CMG, which communicate each other's by the on-chip network by the MPI. But network on chip here support the memory coherence between the CMG. So you can run 48-thread OpenMP program using the all core. This is the photograph of the A64FX chip die. Here, this is the core. And you can see the cores are grouped in this CMG. The network interface and the PCI interface is integrated in one chip. Chip and the HBM chip are mounted on a silicon interposer connected by the TSMC core technologies. It might be interesting to compare die size with another processor. This is the die photograph of the Skylake. Die size is the little bigger than ours. Skylake has just only 18 cores. As you can see, die of the A64FX is the more than 3 times smaller than Xeon 1 per core. I'd like to show you some benchmark result and performance characteristics of the A65X processor. Cloverleaf is a benchmark taken from the UK benchmark. The workload is the typical stencil application. This is the result of the Cloverleaf comparing to the Cavium SandX2 and Intel Skylake. The one process is running on one socket in case of the the SandX2 and Skylake. And in case of the A65FX processor, one MPI process is running on one CMG. The left-hand side graph shows the execution time, and right-hand side graph is the relative performance to the one cores of the A65X. As you can see here, it shows the good scalabilities by increasing the number of threads within a CMG, within a chip here. And the Skylake has just 12 cores per chip. So one CMG performance is comparable to the Intel one socket. The A65FX has the 4 CMG in one chip. The several HPC open source softwares were already ported and evaluated. This graph shows the performance and the power efficiency of the open source application using one chip A65X and the dual chip of the Xeon. Here is the name of the open source application. As shown in this graph here, this is the blue one is the execution time, and red one is the average power. So as shown in the graph, the almost same performance to the dual socket of the Xeon with half power consumption. The performance of the A65X is not always good. This is the result of the Lurish, the unstructured mesh application from the US benchmark. This result is taken from by evaluating using the one CMG and one chip without MPI. One CMG performance is less than the SandX2 and the Intel one. So we found that the low vectorization and the ratio of the SIMD instruction is just a few %. So we think we need more code tuning for more vectorization using the SIMD. To improve the performance of the sparse matrix code like Lurish, it's known that storage format is very important. So this paper is reported sliced ELL pack format shows the very good performance, and the CSR is not so good even by manual vectorization by the intrinsic. And we found that this is the number of threads and memory bandwidth. So we found that vectorizing the SPE is also important to get the memory bandwidth. Okay, let me show the result of some of the spec benchmark. Spec benchmark is a very famous industrial benchmark suite. This is the result of the spec CPU base int speed for each benchmark and total index. So we compare the A64FX with the Intel Xeon processor. The almost benchmarks is run on a single thread, and the single thread performance is of the integer of the A64FX is about in 1/4 of the Xeon. It's not so fast. The reason for the low single the integer performance of the A64FX is that similar rate is low in these benchmark, the spec int. And also the frequency and out of the resources are very limited due to the throughput-oriented architecture of the A64FX processor. And this is the result of the spec OMP. This application is almost a scientific workload. So we compare the A64FX to another Xeon processors, the Cascade Lake. Yeah. The performance of the A64FX using the 48 thread is about the 5% performance of the Xeon using the 56 thread and 28 cores. For some benchmark, here, SIM and MGrid, the A64FX result extremely good performance than Xeon because of the high memory bandwidth of the HBM2. But some application, like the MD, the performance of the A64FX is extremely bad than Xeon. The performance, but we found the performance improvement has confirmed by source code tuning, like loop inlining and loop unrolling. So we hope that this kind of the performance tuning is supported by the compiler, by the improvement of the compiler. So let me summarize the performance characteristics of the A64FX processor. For core-to-core comparison, the integer performance is not so fast, the 1/4 of the Xeon. And the chip-to-chip comparison in a spec OMP benchmark. So 48 performance of the one chip is 65% of the Xeon. But please note that performance of the memory intensive application is extremely good, thanks to the HBM2. And as I shown at the beginning, and for some scientific workload, like HPOSS and UK benchmark, the almost same performance to the dual socket of Xeon with half of the power consumption. And I pointed out the high simile rate is very important to get a performance. To do that, we need some the code tuning to for the memory access pattern, and unfortunately, the many benchmark are not yet well vectorized. And the power efficiency of the A65 is very good. Next, let me show the overview of the software, system software of the Fugaku. This figure shows the overview of the system software stack of the Fugaku system. The operating system is based on Red Hat Linux. So, and thanks to the ARM ecosystem, the many applications may work with a simple recompilation from x86 Red Hat Linux environment. So open source software is already available by the SPAC package manager managing software, the software. As I told at the beginning, standard programming model is the OpenMP plus MPI. So two MPI is available. One is the OpenMPI by the Fujitsu and impeached by the Riken. So you can use the four kind of the compiler and a low-level communication library for the TOF network is provided. And as for the container and the virtual machine, the Singularity is supported. And as for the deep learning framework, DL4 Fugaku is developed by the collaboration by the Riken and ARM and the Fujitsu. So by using this framework, you can use the Chainer, the PyTorch, and TensorFlow. And several softwares and the programming language mass library is developed by the Riken. So MC kernel is lightweight kernel. And SQLMP is the PGAS language. FPDPS is the framework for particle simulation. And AngenExa is the eigenvalue mass library for the large scale system. So let me talk about the performance tuning a little bit. So A65X took the HPC-oriented design, the small core, and less the out of the resources shown in this table. And the pipeline is relatively long. So architecture is high throughput, but long latency. So this causes sometimes the pipeline stalled for the loops having complex body. So to relax this restriction, software pipelining and the loop efficient by the compiler is sometimes effective. So as you can see, this is a result of the Livermore benchmark. So up to the 20% performance improvement by the software pipeline. A65X has several power mode, boost mode, and echo mode. The clock frequency can be raised from the to the 2.2 from 2.0 in the boost mode, and we can reduce the power by stopping the one simile pipe in the echo mode. So this graph shows the the power and the power consumption, the power and performance of the stream benchmark using the echo mode. So performance is almost same as that in the normal mode, but 20%, 20 to the 25% reduction in the power comparing to the normal mode here. The graph, bar graph shows the power, and the green line graph shows the performance. So this is the concluding remarks. So we have confirmed the 3 KPI here: power efficiency and effective performance application and ease of use. So this table is taken from the RCCS website about the Fugaku. This table, in this table, target performance has been achieved. And as for the power consumption, this lower power consumption, we estimated here. And we found that in daily operation, the system power consumption is around 20 megawatt with the 70% of the utilization. So system is the very, very the power efficient system. And I presented the characteristics of A64 FX processor. That this processor is the many cores and small cores and less out of resource to reduce the die size. So integer performance of the core is not so high, but for some memory intensive application is extremely good thanks to the HBM. So thanks for your attention.